In today's video, we're going to cover weight transfer and some basic dynamic characteristics of your vehicle. We're going to be covering the lateral and longitudinal weight transfer, the roll moment acting on the vehicle, the force acting independently on each tire, the force acting through suspension system, and a sprung versus an unsprung mass. To start off, let's just define some of the basic sign convention here. We're going to be saying that the y-axis is going lateral relative to our car, the x-axis is going to be longitudinal along the car, and the z-axis will be facing down vertically on the car itself. You'll see this pop up when we're concerning about the force acting in the y, z, and x direction. The z force being the vertical force applied to the tires, the y force being the lateral force that the tires are capable of generating, and the x force being the longitudinal force that the tire is capable of generating. So first, what do we define as a sprung versus an unsprung mass? So a sprung mass is any component that has a mass behind it that is directly attached to your suspension system. So this would cover your wheel, being the rim and the tire, wheel hubs, the bearings, your upright, control arms, any suspension components like a push rod, a bell crank, or the damper and spring assembly. And your unsprung mass is going to be components that are not directly linked to your suspension. So they don't directly move when a force is applied onto the tire. So this is going to be your chassis and everything inside of it, essentially. So that would be the bulk of your weight is an unsprung mass. The chassis, the accumulator, your driver is an unsprung mass. And when it comes to doing weight reduction, which is one of the key characteristics of a good vehicle design, you want to be looking at reducing your sprung mass primarily, and your unsprung mass is less so important, although both are still beneficial to remove mass from. But reducing a small amount of sprung mass is the same as reducing a large amount of unsprung mass. The reason behind this being that your sprung mass is directly connected to all of the moving parts that respond to changes in the road surface and changes in your car's handling. And so if you were to go over a bump on the front left wheel and it shifts that wheel upwards, there's a period of time in which all the components have to move through the cycle, and the heavier they are, the longer this time takes, and thus the slower the response to your suspension system. Whereas you want your suspension response to be as quick as possible to changes in the road surface to accurately absorb any of the forces coming through and keep your car nice and stable. And additionally, when it comes to just longitudinal acceleration, there is a moment of inertia applied on your wheel, and you have to overcome that inertia in order to accelerate the car. And that rotational inertia, lowering that will increase your acceleration massively versus just lowering the overall weight of the car. Lowering weight in both cases is good, but lowering your sprung mass will generally have a more noticeable impact than your unsprung mass. So first, let's look at the longitudinal transfer, which is our simpler type. So longitudinal transfer is defining weight shifting forward and backwards in the car, essentially. So you'll be seeing this in any situation where the car is accelerating or decelerating. This could be in a straight line when you're just on the gas or on the brake, or it could also be in a corner when you're slowing down through the corner or speeding up at the corner exit. Longitudinal transfer is going to be a shift of mass from the front tires to the back tires. Not a shift in mass per se, but a shift in applied weight. So an applied force on the tire. Simply put, when you're accelerating, you'll have weight shift to the back of the car and more force on the rear tires and less force on the front tires. Whereas when you're braking, weight is going to shift to the front of the car, applying more force to the front tires and less force to the back tires. When we look at this in terms of mathematics, what we're concerned about is the positioning of the tires and the position of our center of gravity. The longitudinal force is going to be equivalent to the entire mass of the car relative to the acceleration that's going at. So it's just the F equals ma formula, looking only at the longitudinal, so straight line acceleration. And where this force acts is going to be on your center of gravity for the entire car, including the sprung mass and unsprung mass for this situation. And what we're going to look at is the height of the center of gravity relative to the bottom of your wheel surface, or the ground surface where your wheel is in contact. There is a moment applied to the bottom of the wheel where the force is applied to the center of gravity and creates a moment around the wheel contact patch. So if we take the balancing equation for this moment, we end up seeing that the change in weight on either the front or the rear tire is going to be equal to the longitudinal force, which is a characteristic of your longitudinal acceleration, multiplied by the height of the center of gravity, that's your h value there, and divided by your wheelbase, which is your b plus a. We're defining a as the distance between the front wheel to the center of gravity and b from the back wheel to the center of gravity. We could just replace this by L or wheelbase, put that on the bottom. We have it written as b plus a right now. And then your force is obviously going to be the mass of your entire car, m, multiplied by your longitudinal acceleration, which is ax. And this will create a moment around the bottom of a tire with the force applied to the center of gravity, rotating around this direction or other direction, depending if you're accelerating or decelerating. And that moment balance will define how much force can be transferred to the back or the front tire. Any force that you see increased on the rear tire, you will see an equal distribution increased or decreased on the front tire, or vice versa. Hence, you can say that the change in force in your back tire is equal to the negative of the change in force on the front tire. When you consider, this is just a change of force. When you consider the total force, you have to account for the weight of the vehicle weighing down on each tire as well. Your vehicle will have a weight distribution. We can say it's 55% on the front, 45% on the rear. It will be different depending on how the vehicle is set up, but this is a value that you should know going into the calculation for it. And so this is your change in force, and you add that to the nominal force already exists due to the mass of the car itself. So if we had a 55% front weight distribution, we would say that the total force is equal to this change in force plus 55% of the weight of the car applied onto the front axle. And then you have to remember you could divide this force evenly between the left and right tire only if you're accelerating purely in a straight line and no cornering force. If you're cornering as well, the force will not be divided up evenly between the two tires, and we'll get into that on our next topic here. So for lateral weight transfer, we're looking at in a cornering situation. Let's assume pure cornering right now with no longitudinal acceleration, and so you're only seeing weight transfer between the front and left side, the right and left side of the car. So we'll see a very similar situation to longitudinal acceleration, the difference being instead of moving from front to back, now we're moving from right to left or left to right, depending on which direction your corner is taking. We're now concerned about the lateral acceleration component, which is the acceleration of the car towards the inside of the turn radius. So if you're taking a right-hand corner, you're seeing lateral acceleration. Your car has to travel in the right direction. You're seeing a reaction force in the left direction, and you're going to transfer weight to the left side of the car. Remember to think of that in terms of reaction forces, not the acceleration of the car itself. And so when we have our lateral acceleration, we're applying a reaction force once again at the center of gravity, and we are very similar to the longitudinal case, concerned about the height of the center of gravity relative to the wheel's contact patch to the ground. We take the moment balance around this contact patch, and we get a very similar equation to a longitudinal, which is the lateral force or lateral reaction force multiplied by the height of the center of gravity and divided by your track width, which is the distance between the two tires here. And that will give you the change in force applied on the one side of the car, right or left. Once again, it's an inverse force, so if you increase the force on the right, you're going to decrease the force on the left by a proportional amount. And you're also getting a lateral acceleration force that's proportional to the mass of the car times the lateral acceleration. Where a lateral acceleration, this is your centripetal acceleration around the corner of a given radius for a known velocity that you're traveling at. This is your straight line velocity here. But we can't consider this quite as evenly as a longitudinal force. Even in a situation of pure lateral weight transfer, we will see the back and the front of the car perform a bit differently. So if you're to take the transfer force between the right and the left tires at the front, you're going to see a different amount for the front and left tires at the rear due to the suspension geometry in the car and what is defined as your roll center as well. It's your RC moment there. We'll get into that in just a second. So if we were to divide the front and rear of the car, so we analyze these as two independent scenarios. So we're looking at force transfer from the front left to the front right wheel, and we're also looking at it from the rear right to the rear left wheel, and we have to treat these as independent cases. So some things to consider here is that you have your center of gravity of the entire car. However, the height of the center of gravity only stays true where the center of gravity actually is, dead center in the car. But if you're to look at just over top of the front axle or over top of the rear axle, the center of gravity for that portion of the vehicle is not necessarily at this height. So we have what's called the centroid axis here, which is a red line running through our car, which shows a rough representation of how the center of gravity migrates when you look at the front to the back. So it's no longer the true center of gravity because we're not lined up longitudinally, but over top of the front axle and over top of the rear axle, the mass will be concentrated differently. If we only consider mass on the vertical concentration here, the centroid, we'll refer to it as, will be at a different height than the actual center of gravity. And so this comes into our consideration when we're calculating for roll, is where the centroid actually exists at. The force will act at the centroid rather than the center of gravity itself when we're calculating our roll moment for later. But right now, let's just look at the weight transfer. So we also have the roll centers here on the car. So the roll center is defined as the point at which the forces acting on the sprung mass rotate around. So whereas the entire mass of the car itself you can consider acting on the center of gravity, if we consider only the forces generated by our sprung mass, that's going to act at our roll center instead. The definition for finding a roll center is the intersection point between two instantaneous centers on the car and the tires acting on the ground. The instantaneous center is defined by your suspension geometry, and this is where your control arms converge. If we were to draw a straight line between our control arms, they should converge at our instantaneous center here, and this is essentially a point of zero velocity on the car, where when the vehicle is rotating, it's rotating around that point. Or more specifically, this mass system here, this sprung mass, is rotating around this instantaneous center. Likewise, this sprung mass here is rotating about this instantaneous center. That's like its center of rotation, its axis of rotation. The intersection between our tire and the instantaneous center, where these connect, that's what's defined as our roll center. And this is where you can define your sprung mass forces acting, whereas the unsprung mass or the entire mass of the car combined will act on your center of gravity. So knowing this, we can define the height of the roll center at the front and the height of the roll center at the rear, and then an axis between the two of them, which we refer to as our roll axis. You should note that as your suspension moves, these instantaneous centers will move as well, and the roll center will then migrate. So this is not a constant position. This axis will shift as the vehicle moves around. We are only considering right now the nominal position. So when the vehicle is at its static resting height, if you consider as a non-moving surface, then we can define our roll center in one place, but this migrates as the car moves around. For simplicity of calculation, we'll consider it as if it acted on only one point right now. If you want to have a more predictable vehicle in terms of calculations, you would design it so your roll center does not migrate that much, but it's impossible to have it stationary. It will always migrate to some degree, and this should be taken into account for in your design process. So now we know the height of the roll center at the front, the height of the roll center at the rear, and the difference in height between the center of gravity and your roll axis. These are our most concerning factors. Finally, we also need to know the roll stiffness at the front and the rear of the car, defined by our Kf for the front and the Kr for the rear. This is defined in the amount of newtons that it requires to roll the car 1 degree or a portion of a radian, depending on which numerical system you're going to use. So it's either newtons per degree or newtons per radian. So we can say the roll stiffness is it requires 800 newtons to roll the car 1 degree. That would be your roll stiffness for the front, and it'll be something different for the rear. This is determined by the suspension geometry itself and the strength of the springs, the anti-roll bar, and the dampers used in the vehicle. So that will require some more in-depth knowledge, but for now, we can consider that this is a known factor for your car. This is something that you'll be able to come up with in your design process and then use that when you're calculating your lateral weight transfer. So if we look at only the front of the car here, the change in your lateral weight, or the force acting down on the front of the car, you need to know the mass of the whole vehicle just times gravity, for that's the nominal weight, so the amount of weight that you always have on the car itself. You need to know the front track width, that's your WF term, the difference in height between the center of gravity and the roll axis, that's your H term, the front and the rear roll stiffness, that's your Kf and your Kr terms. B is going to be the difference in length between the rear wheel and the center of gravity. L is the entire track width here, and RCF is the height of your front roll center. We see a similar equation down here for the rear of the car. Once again, this is just change in force, not the total force itself. Very similar, other than the fact that we're switching up the roll stiffness in there, and also the length between the front tire and center of gravity instead of the rear tire and center of gravity, and also rear roll center. Knowing these, we can now calculate independently what is the force moving on the front of the car, what is the force moving the back of the car. And so the amount of lateral weight transfer, the equation we looked at before is for the total amount of lateral weight transfer. This divides it up front and rear, so you can independently see what does the front tire receive, what does the rear tire receive when we split up the equations. So this is more important if you're actually going to consider how much force your tires are capable of generating. Knowing these numbers front and rear independently is an important factor in knowing, are you using the full capabilities of the tire, and how much lateral force is that tire going to be able to generate. you can't just assume that the entire weight transfer will be split evenly between the front and the rear and use that in your lateral force calculations. You'll end up with inconsistencies and you'll most likely not be using the full potential of your tires. Rather, you want to consider these systems independently. And next, we're going to look at some of the forces exerted in a corner as you go through the car. We're no longer considering just a static system. Now we're considering the car moving around the corner and how the forces are generated through that. So we're looking at this as if it was a two-wheel system here. So we can consider that the car is just acting on, we're considering the front track as one wheel and the rear track as one wheel. I'm not going to divide it up between the two. For simplicity's sake, this won't return 100% accurate results, but it is a good enough representation of how your forces are generated in the vehicle. Shown with the blue lines here are the paths traveled by the front and rear wheel. As you can see, they don't perfectly coincide. The steering geometry that you set up will affect how close these lines are together and what point they intersect at. In this situation, we're saying that they're not going to intersect, they're going to run concentric to each other, but they don't follow the exact same path. The AF and AR here are the slip angles of the tires, which we covered shortly in the last lecture. So the tire itself, the path that it travels is slightly different than the orientation of the tire. That will be your slip angle, and this is important in knowing how much lateral force your tire is capable of generating. We have the turning center here, and this is sort of the center of the path that the car is following around if we were assuming that it was a constant radius. There's your turning radius, and the angle theta from this bottom line here to the top line, which is perpendicular to our tires, that is going to be equal to the track length of your car divided by the turning radius. That will give you the angle. This is using the small angle assumption. So this doesn't apply for large angles, let's say 20 degrees and above. This would no longer really hold true. This is an approximation using small angle assumptions. So you need to consider that you have a centripetal acceleration acting on the car in order to turn it around this turning center. That's going to be dependent on the traveling velocity of the vehicle. If we were to consider a velocity acting on center of gravity as being straight or tangential to the path that the car is traveling around, that would be your linear velocity. You can use that and turning radius to get your centripetal acceleration. Knowing that, you can also determine what's the reaction force acting on your center of gravity. And so the force acting on the center of gravity will be equal to the total mass of the car multiplied by the centripetal acceleration. And then dividing that up, you can determine how much lateral force you need in the front tire, how much lateral force on the rear tire. And force balance on that will be the lateral force on the front plus the lateral force on the rear needs to be equal to the lateral force acting on the center of gravity in order to keep your system balanced for a steady state situation. You also know the turning moments around the center of gravity based on the distance between the center of gravity and its front tire and the center of gravity and the rear tire lengths A and B there. You can use a moment balance and these two forces to get your moment balance. From all of that, you can determine what your front force and the rear force are. And using your quartering stiffness here, your CF terms, this should be a CR there actually, I might correct that later. It should be a CR term on the bottom there. Using that and the known lateral force that you need, you can figure out what the generated slip angle of your tire is. The cornering stiffness, the CF and CR terms, will be a known parameter for the specific tire. That's going to be dependent on the tire characteristics, and you need to use some data analysis to figure out what those are going to be. And you can use that to determine what slip angle you're going to be generating at the front and the rear tire. And if we consider cornering as a moving force, it's not always a steady state situation. The equations shown in the last slide are a simple state. For a steady state corner, we're moving at a constant velocity around the corner, and we're also, the corner itself follows a constant radius. In realistic situations, we're going to be following a dynamic cornering state where our velocity is changing as we go through the corner. Thus, we need to be more concerned about the accelerations that we're undergoing, so the linear acceleration and how that translates into our cornering acceleration down here. And this is a much harder state to analyze, so we're not going to put all the equations down here. This is something you need to go through on your own at some point and get a more in-depth understanding of the equations. But the general idea here is that we are now concerned with the moment that we're generating around this turning center. So the car is still following that same linear path here along velocity b, turning about the center of your corner here. For that point, what the corner radius is. The corner radius may change as you go through. It's easiest if you consider it to be a constant radius and you get that static turning center. And the moment generated around this turning center is now going to be a function of the angular acceleration, which is our omega prime term here, so the derivative of omega being your angular velocity. You need to know the angular acceleration and the moment of inertia through the center of gravity of your car, which is your z term there. And this is applying a torque about this point, or we refer to it as a moment in this situation. And the higher the moment that you're generating here, the faster the turn is going to be, essentially. But likewise, you want to minimize the amount of moment that you need for a given angular acceleration. The way you do this is by lowering your moment of inertia in the car. If we consider that we want to go, let's say we wanted to accelerate at 2 radians per second squared, which would be your angular acceleration term, that's going to give us a moment that we need to be able to generate in order to make the car follow that path. The only way we're going to be able to reduce that is by decreasing our moment of inertia. This can be done either through just general weight reduction, will decrease the moment of inertia, or the weight distribution of the car as well. How close to the center of gravity you have all that weight concentrated is going to affect the moment of inertia going through your center of gravity. And so not only do you want to consider weight reduction in the vehicle, you want to consider weight placement and how close you can get that to the center of gravity to reduce your moment of inertia. The lower this is, the less force you will require in order to go around the given corner. And that will be able to increase your centripetal acceleration, your angular acceleration, or it will just decrease the force required by the tires. So once again, we're creating this moment here where we have the front force and the rear force multiplied by the length from the center of gravity will give you the total moment that you're capable of generating. So if you say the front tire is capable of generating 1200 newtons of lateral force and the rear tire is capable of generating 1000 newtons of lateral force, from that we know how much of a moment the car is capable of withstanding. And from that and the moment of inertia, we can figure out how tight of a corner can we take with that. The higher our angular acceleration is here, the faster we're able to go around a given corner and the tighter of a corner we can take. And so if we consider that we're limited by how much lateral force we can generate, the tire can only do so much. If we want to take a faster corner, we thus have to decrease our moment of inertia here. And then we also have the force balance. So we have the moment balance up top and the force balance down here, which is the mass of the car times the centripetal acceleration. And if we want to break that down further, we get the mass of the car times the linear velocity multiplied by the angular velocity plus the rate of change of slip angle of the vehicle. So as we know from before, we have a slip angle acting on the tires on the front and the rear. We also have a slip angle acting on the center of gravity itself. So the path that the car actually travels along the velocity vector v versus the longitudinal line through the center of the car, that will give us our slip angle for the whole vehicle. And the rate of change of this slip angle is going to be a function of how fast you're taking that corner and how tight the corner is. And that will affect how much force you need to generate towards the inside of this turning radius, with the reaction force being outwards. And so the general idea here is that you're limited in how much force you can generate at the front and the rear. The amount of moment that you're able to create is going to be a function of both that and also the front track width and the distance away from the center of gravity for the front track and the rear track. But the main thing that you should be concerned about is lowering this moment of inertia here. If we know that these are our limiting factors and we can't go through the roof with this, we have an upper ceiling to how much force we can generate. Thus, if we want to go faster through corners, which is a major concern as a lot of your speed is gained, a lot of your momentum is carried by taking corners quickly, especially for autocross style tracks, we really want to focus on reducing that moment of inertia. And that goes over most of what we want to go for weight transfer here. I'd encourage you to do further reading, especially on that last part with the dynamic cornering situations, as there are just too many equations to go through in a short period. You're going to want to be able to read over those yourselves, go through that a lot more in depth, investigate each term independently. The best source for this would be Race Car Vehicle Dynamics, the textbook by Millikan. That one will go through the most in depth, show you all the individual steps, and break down the rate of change of each factor and how it's going to affect how your vehicle handles. It's a fairly lengthy explanation, but it's definitely worth checking out if you're more interested in this subject. In the meantime, this is more of just the surface level understanding, but hopefully everything was delivered fairly clear in this situation.